The first derivative test is a great way to determine if a critical point is a local maximum or a local minimum. You begin by finding a critical point or a critical value, which is the location where the first derivative evaluated at that number is 0, meaning you have a horizontal tangent line or the slope of your tangent line is 0. Then you check numbers around that point. If you notice that the first derivative changes from positive to negative, meaning the function has positive slopes of tangent lines, then they turn to 0 and then hit negative slopes of tangent lines. Or you could think of it as the function going from increasing and then stopping, turning around, and then decreasing. Then that means that value, f of c, is a local maximum. Or if you notice the first derivative changes from negative to positive, meaning the slopes of the tangent line go from negative, hit 0, and then turn positive again. Or you think of it as the function changes from decreasing to increasing, then that f of c, that value, is a local minimum. Let's take a look at an example here. Let's find the local extrema, which is another way of saying find the local max and the local min for the function using the first derivative test. We will begin by finding the first derivative, f prime of x, which is equal to 6x squared minus 6x minus 12. Set this first derivative equal to 0 so that we can find the critical values. 0 equals 6x squared minus 6x minus 12. This equation is easier to solve if we divide each side of the equation by 6. 0 divided by 6 is 0, equals x squared minus x minus 2. Factor this equation, x minus 2 times x plus 1. Set each factor equal to 0 and isolate the x value. We will find the x value could be 2 or negative 1. These are the critical values. These are the location where the first derivative is equal to 0. I like to plot these values on a number line. And we know at these values the first derivative is 0. And here comes the first derivative test. You're going to test in the first derivative numbers around those critical values to get an idea of what's going on with the first derivative. We can begin by numbers to the left of negative 1, let's say negative 2, and plug in that number into the first derivative. We will find f prime of negative 2. And this will become 6 times negative 2 squared minus 6 times negative 2 minus 12, which is equal to 24 plus 12 minus 12, which is 24. The important part to note is that this is greater than 0, meaning we got a positive value for the first derivative. To the left of negative 1, we tested that the first derivative is positive. Now let's test the first derivative between negative 1 and 2. We can plug in the number 0, which is in that interval. Let's plug in 0 into the first derivative, and that becomes 0 plus 0 minus 12, which is negative 12. The important part is that that number is negative. The first derivative at that value is negative, so I'm going to mark that on the number line that f prime has a negative value there. And then if we plug in a number to the right of 2, something sufficiently larger than 2, let's say x is 100, it's not too hard to determine that the first derivative is going to be very positive. Here comes the first derivative test. If you notice at that critical value negative 1, f prime goes from positive to negative, meaning the function would go from increasing to decreasing. That means at that value, at the x value of negative 1, we have the location of a local max. You can also think of it as f of negative 1 is a local maximum value. Similarly, at the location of the x value of 2, to the left, the derivative is negative, and then it turns to positive. The function would go from decreasing to increasing. Then that x value is the location of a local minimum. And that's how we interpret the first derivative test. Let's take a look at the graph and see if we can verify these results. Here we have the f of negative 1 being the local maximum value, and the maximum value is the y value of the function, because to the left we have the function was increasing with a positive derivative, hit 0 at that critical value, and then decreasing with a negative derivative that confirmed a local max. And then the f of 2 had a first derivative turning from negative, hitting 0, and then changing to positive to go from decreasing to increasing. That's how we confirm that f of 2 is a local minimum.